Great, thank you so much. All right, welcome everyone. All right, let's dive into it. We've got a lot to cover, so let's get right into it. This is the leader, right? This is the spoiler. We're now GA as of today. So, yeah, 3 years at MongoDB and probably 20 in the academic space, so big day for us. All versions of MongoDB, so Atlas, we're bringing on serverless shared in the free tier soon, very, very soon. Enterprise Advanced and the Community Edition, as of today, Queryable Encryption's GA. All the major drivers, so pick your favorite language, we're shipping. Compass and Mongo Shallow support as well. So what is this encryption stuff? So here I covered a little bit, but I'll do a quick recap. So when we're deploying applications to the cloud, a lot of these terms are pretty standard. I mean, they're almost table stakes, frankly, right? We know about encryption in transit. We want to protect from surveillance and eavesdropping over the network, so we use TLS or HTTPS, et cetera, or VPNs. We worry about volume encryption, storage encryption, right? So that's, it's more a concern for data centers. I don't think too many people are concerned about someone taking a hard drive out of Amazon. But if you do have a backup or a snapshot of your system, encryption at rest is a really useful control. So if you think about the life cycle or the data flow of an application, you've got developers, the client application, the database, and then the storage, right? So one thing that we don't talk about very often, and I think even a lot of like senior technologists, and frankly even a lot of CIOs are kind of unclear on this. There's a lot of discussion about I own my keys, I manage my keys, I'm using encryption at rest, and so my data is encrypted. Well, your data is encrypted when the database isn't running. But I don't know about you, my databases are really useful when they are running, when they're up and listening to the network, right? The client application, by definition, that's the source of truth, right? That's, if you're talking about PII, if you're talking about social security numbers or credit card numbers or other kinds of sensitive information, that's the source of origin, right? That's where clear text starts. So that's okay to be unencrypted there. It's a trust problem, though, right? Because we have data that's really sensitive. We either manage it ourselves in a data center, or we self-manage on the cloud, or we use a service like MongoDB Atlas. There's an element of trust in it, right? So with Queryable Encryption, one of the things that a lot of customers talk to us about is, it's not that we don't trust you, but we have an institutional risk posture where we can't trust you. We can't trust the service provider, we can't trust the underlying cloud provider. If someone comes to one of our own DBAs and says, here's a suitcase full of cash, I need information on these records. And we have customers where the volume and the sensitivity of their financial data, that's not a theoretical concern. They really do care about inside attacks. But for most of us, we worry about sort of the traditional stuff, right? Breaches, leaks, accidental exposures, just human mistakes as well. That's one of the things that Queryable Encryption is designed to address. Right? So one of the key killer benefits in my view of Queryable Encryption is when the database is operating on completely encrypted data, when it's blind to the information it's holding, wouldn't it be great if we could actually do things like, I want to know all the customer records where the age of my customers is between 18 and 27, or I want to know, in a financial fraud case, I want to know all transactions that were between $1 million and $700 million, or between these values, these financial values. I'd like to be able to do prefix. If I start typing a name, a long name, it'd be nice to complete that automatically. If I had a suffix, like final few numbers of a card number, it would be really great if I could query on that without having to do the whole thing. And lastly, what if we could actually search on substring, right? What if we could search on text values within a larger text record in a way that the database can't see it, in a way that while it's literally being operated in memory, that the database can't see it. And that's what Queryable Encryption brings us. It's fully end-to-end randomized encryption, which means from the point of the application boundary all the way to the database, whether TLS is somehow compromised or broken or misconfigured, if the volume encryption on the database is broken, if someone gets access to those records, it doesn't matter because the data are completely end-to-end encrypted. They remain as ciphertext from the point of the application all the way back to query time. Groundbreaking technology. So if you've been following any of the academic world in what's referred to as encrypted search or private query, this isn't new. Some of this has been around for 18, 20 years. What is different, though, is in most of the academic literature, the models say, I've got one laptop and one database server, and there's one user. And there's a long paper of that. You sort of raise your hand and say, well, wait. What if you have lots of users? What if you have concurrency? What if you have contention? What if you have, distributed systems? How does that work? Most of the academic sort of models sort of fall apart. What's really exciting about queryable encryption is we took what was fundamentally mature technology in terms of the core cryptography, and we productized it. And that's what this talks about. Strong technical controls. It's important for a service provider to say, in a contract, in contractual language, we meet these service level agreements. We meet these obligations. That's critical. It's important for organizations to have administrative controls, right? So you shouldn't do this. If you do, if you peek at this customer data, if you look at these records, you could get in trouble, you could get fired, you could go to prison. Those are good controls for sensitive systems, but they're not technical controls. A technical control is a way that we can ensure that certain parts of the data path are completely oblivious, and that's what we're working on. Faster app development too. I don't know if you've looked at some of the existing solutions in the software development kits for some of the big cloud providers for certain languages. There's no shortage of options for developers to sort of encrypt sensitive data. But in nearly every case, what happens is, let's say I've got sensitive PII. The solution is, okay, take that, AES encrypted, stuff it in the database, and then you can't do anything with it. You can retrieve the records back, but you have to bring all of them back. You can't search for things that are encrypted. You've got some degree of confidentiality protection, but you've lost an enormous amount of practical flexibility. And again, reducing institutional risk. We have customers in the capital market space that are moving hundreds of millions of dollars through our platform. That is a level of sort of data stewardship and obligation that's just on a different plane than a lot of other customers. We have customers where if there's certain breaches that exceed a given number of records in a region, they're out of business. They have to shut down. And so all of these kinds of things, these sort of security controls and considerations are part of a strategic view of how do we make really good use of our data and make application development easier for developers, but still maintain strong protections. So queryable encryption, you encrypt the sensitive data. Usually those are individual fields. So let's say in a customer contact record, it may not be sensitive that there's a zip code. It may not be sensitive of a certain geographic region. Gender may not be sensitive, but you certainly think about things like phone numbers, bank account numbers, credit card numbers, et cetera. Queryable encryption allows you to do rich, expressive queries. And again, it's encrypted throughout the life cycle. And you don't have to be deeply versed in cryptography, right? You shouldn't have to think about, well, do I use this key exchange scheme? Do I use this cipher suite or that cipher suite? Or if I do this one, is it going to leave me vulnerable in some way? Or is this one sort of going to be kosher with our, with our security compliance team? Does it meet some of the requirements we've got to deal with PCI or HIPAA, et cetera? And you certainly shouldn't have to have deep security cryptography experience in terms of, the lower levels. It's a fairly opinionated framework that says you identify the fields that you care about, and they're going to be protected with strong modern protocols. Let me go forward, because we've got another slide, I think, that does a little better job of this. How's this different from other solutions? We get this a fair amount. Customers who have sort of evaluated or taken an early look, they said, well, is this something like homomorphic encryption that I've read about where, there's a type of low-level cryptography where you can still perform and compute operations on encrypted data? No. Homomorphic encryption has a lot of great use cases. What it's not terribly well designed for is general purpose search in a database of hundreds of millions of records. And also, one of the sort of core problems with FHE is that the search speed is linear. That is, if I have 1,000 records, I get a certain performance. If I have 10,000 or 100,000 or a million, I start having supralinear query results, which means I could be talking seconds or minutes or hours. That's just not realistic in an operational data store. Again, there are some great use cases in private computation, but for databases, FHE is not a great solution. Secure enclaves is something, too, that we see a lot of discussion around. Fundamentally, secure enclaves, when you dig into it, it's a hardware, a trust execution environment where there's clear text at some point living inside the chip of a service provider. This is not that. You can certainly use something like secure enclaves on the client side if you worry about application level attacks. You want to sort of raise the bar a little bit, I guess, for how you manage keys, but that has nothing to do with the database, right? So let's take a step back for a second. So just to remind you, in so in 2019, we released the client-side field-level encryption. We'd been working on it for about 2 years before that. One of the groups that we had worked with, let me take a step back. One of the decisions that we made early on when we first looked at our first generation end-to-end encryption was this notion that, we're pretty good engineers. We have hundreds and hundreds of engineers at MongoDB. We're pretty good at distributed systems. We are not cryptographers, though. And we've seen enough failures in other products. You look at browsers, you look at the history of TLS bugs, et cetera. There can be really subtle implementation mistakes. It can be really subtle leaks of data that can completely undermine the protections that you're looking to put in place. And so we said, well, look, if we're going to build this into the product, why don't we engage people who are experts at breaking encryption? Why don't we engage people who are experts in encrypted search? Why don't we engage people who are both cryptographers and understand security engineering? So they can look at things like buffer overflows, and are we doing key management sanely? Is our TLS library, does it make sense with the major key providers? Those sorts of things. And so one of the groups that we worked with was this team out of Brown University, the Encrypted Systems Lab. It was headed up by Seni Kamara and Tariq Mohdaz. They'd been working on encrypted search for years. And so they helped us think about our threat model. They helped us think about what we could sort of, what security guarantees we could make, what we couldn't make. They helped us tweak the design a little bit. And that was a great collaboration. But when we, so after we launched the client-side field-level encryption, we continue to stay in touch. We continue to collaborate. And in that time, some of the work they were doing, they had sort of a major breakthrough. They figured out a way to maintain blinded database state without having to maintain caches, right? So if you're a Python or a Java developer, it's hard enough to write a secure modern web app, right? You don't want to have to get into the business of thinking about a distributed client-side cache. And yet a lot of the academic models, that's exactly what you'd have to do. We looked at what they'd come up with and said, well, this is seriously a game changer. We continued talking, and eventually their commercial spinoff from their work there, Oroki Systems, we decided to acquire. We brought them with us. They're now at MongoDB. And we have an in-house cryptography team of, I think, 5 PhD cryptographers. We have visiting scientists, students. So this is a major strategic investment that we've made in advanced security. Last year, we introduced the Queryable Encryption preview as a beta. We said very clearly, we're going to be making breaking changes. We're going to make this, backward-breaking changes. Do not use this in production. We're going to be tweaking the performance. We're going to be making some changes to the fundamental search structures. Do not use this in production. But it was a great opportunity for us to work with customers who were using this in real-world applications. Right. So as of today, with 7.0 launch, we are now GA for Queryable Encryption, and we've got big plans too. So the initial launch today is on the core framework, it's on the drivers, it's on the supporting Compass and Shell, and then we've also got sort of the core framework that lets us build onto these other types of expressive queries that I mentioned. We don't have it here, but one thing I should say is it's probably not much of a stretch to imagine what an in-house crypto group is thinking beyond just a particular feature. So stay tuned for lots of interesting work ahead in the privacy-preserving tech world from this group. Okay, data flow. I think this is a little easier to follow. So let's say we have an application. It's a pretty straightforward traditional MongoDB query. db.billing.find, give me this social security number. When Queryable Encryption is enabled, the driver will take that, look at it, and say, you know, I need to get a key that's, that's tied to this. I'm going to go fetch it from a cloud provider or your key management service. I'm going to do some work. I'm going to take that document that's been encrypted and lives in the database. I'm going to send a cryptographic token to the server. There's a type of encrypted search structures. There's sort of functional indexes. This is the cool part. Not only does the database not know that these records are encrypted with, that the clear text value of that record is 901.10.4312. It doesn't know that you're asking for that particular social security number. In other words, in the logs for the query itself, the query is encrypted. But we go a step further. The database doesn't even learn that you're querying SSN in this case. It doesn't know what field you've asked for. All it knows is I've traversed an encrypted map. I got 3 hits. I don't know why they're associated or what the relationship is. Here's 3 encrypted documents. They're returned back. The driver automatically decrypts it and hands it back to the application. So from the developer's perspective, I wrote DB billing fine and SSN, and I get the records back. That's pretty cool. The entire transit of that, storage, transmission, processing, and retrieval is ciphertext, including queries. So what does this mean from sort of a threat posture? If I'm a DBA and I have high-level privileges, I've got privileged network access, I've got high-level credentials, I can get to the database, I can run queries, that's what I'm getting. I'm getting ciphertext. It's only on the application side where you've got those end-to-end encryption keys that you're able to see these sensitive fields. Okay, so some of you may have been tinkering around, playing with it, doing some sort of proof of concept projects. So kind of what's the difference between what we've had for the last year or so versus GA? What's in GA, again, is a core crypto framework, equality comparisons on randomly encrypted data. That's an important piece. So if I have, say, a certain social security number, every time it's encrypted, it's going to be encrypted with a different value. This is not deterministic encryption. This is not tokenization. And in the GA again, Compass and Shell and all the major drivers. So, but really, what have you guys been doing for the last year? We get this question a lot. We've had customers that within a month of the initial public preview were like, we want to put this into production. No, not quite. So what do we do? Well, we worked on performance a lot. We spent 5 months. We got 10 to 100x improvement in certain query loads. The developer experience, one of the things that we got feedback on was key management's a pain. I don't want to have to create my own keys. I don't have to manage them. I don't have to think about them. I don't have to track them. That's a pain. The other is bulk writes. So there are a lot of applications where, like day to day, you're not doing heavy writes. Right? It's like 90, 95% reads and some updates and inserts. But when you're first building test databases, or if you're doing migrations, you may be creating millions of records. And one of the things that we hadn't really sort of focused on too much in the very early release was, well, what happens when I need to write 100 million records that are encrypted with Queryable Encryption? Well, so now we've supported insert many. And in addition to say, multi-threaded or parallel workloads, improvements on the latency and throughput have been dramatic. And I'll get into some specifics in just a second. We mentioned we're going to be breaking changes. We absolutely did. The whole way that our encrypted search maps work have been kind of reworked. And then, importantly, even though we have deep in-house expertise, that wasn't enough. We've submitted peer-reviewed papers. We've had experts who are, some of the best people in the field take a look at this, take a look at our academic, the formal proofs, take a look at the implemented code. We've had third-party security engineering firms look really carefully at sort of the entire life cycle and whether we're doing things in a reasonable way or not. We're never going to make any claims about, hacker-proof or some sort of silver bullet in security, but we feel like it's really important that besides the open cryptography, and it is open source and available to anyone to look at and scrutinize, but we really wanted that extra insight and extra scrutiny. Okay, so some of you may have been playing with the 6x public preview. So essentially any aspect of Queryable Encryption in version 6, will we support that going forward? No, we absolutely will not. That was a point in time preview. So 7.0 is the GA and is stable for production. Other query types coming soon. So I mentioned range. This is integers, dates, decimal 128, so like financial, precision data, prefix, suffix, and then the substrings as well. And so what's important is that we built this foundation. We've got the cryptography framework in place across 12 different languages, and the core query capability is ready to go today. How does it work? Let's take a look. You can do a hello world essentially from nothing to create an encrypted collection, insert some documents, retrieve one back in about 40 lines of code. That took an awful lot of engineering time to get rid of boilerplate. Now, I'll grant you, if you're working in Java, there's still a little bit more boilerplate, but help us out a little bit. But the point is that we've got tutorials, we've got code examples, copy-pastable examples, and then more complex examples as well in all the documentation. One of the things I want to point out, though, is that I mentioned earlier, key management was something that a lot of developers had sort of raised as kind of a pain point. So with this line, create encrypted collection, let's say you had, well, actually in this case, you don't have to imagine. You've got 3 encrypted values, Social Security number, date of birth, and a subdocument called contacts, and within that, one of the child records is mobile number. That's the setup. With that command, we automatically create the collection, we create the functional indexes, we generate individual data encryption keys for each of those, we tag it, and we automatically manage it. The developer doesn't have to think about that anymore. The design goals. So a little bit more kind of on the sort of process and backstory of Queryable Encryption. We really, really focus on fast retrieval. It's optimized for high-speed search. So sublinear search. Whether you have 100 million records, 300 million records, 1 billion records, you're going to see really good performance. Expressive queries with minimal query restrictions. Stateless client, I mentioned the lack of a client-side cache. Non-interactivity, there's a huge MongoDB ecosystem that has established norms on how our network protocol works. We didn't want to mess with that. And as you know, one of the most expensive parts of an application is any transit between a service provider and the database. Concurrency. We went through a lot of work to make sure that if there's hotspots, if there's lots and lots of multi-read, multi-write concurrent users, that we can handle that under a high availability load. Distributed and scalable, that's by default. We just released several papers today that get into some of the details if you're interested in more. I've got links at the end of the slides. In short, we use a novel in-use encryption scheme called OST. It was designed by our in-house crypto group. It uses a structured encryption scheme for document databases that's efficient, non-interactive, stateless, concurrent, and expressive. And it was designed, again, to work seamlessly with our existing architecture. Another view of kind of the flow. Let's assume we've got some encrypted records. We need to get encrypted records. We do an insert by taking the document. It's traditional, standard, boring, kind of authenticated AES encryption. But in addition to that, we generate additional search tokens. Right? We're using a customer-provided key. We send the encrypted document and those tokens to the server. The server takes those. It generates other keys, other cryptographic tags, augments the existing document with one sort of metadata field, and it stores that document. From a DB's perspective, those structured fields just look like any kind of binary data. They're just arbitrary binary data. So when you query it, the crypto library analyzes the query, figures out which cryptographic tokens it needs to be generated. It rewrites the query. Again, as I mentioned earlier, not only does it not see the document, it doesn't see the particular query value, the filter value, and it doesn't, and one step further, it doesn't know that it's being queried on SSN, the given field itself. That's sent to the database. There's, if you're familiar with sort of an inverted dictionary, that's one of the data structures that's used. We retrieve those documents and send those back to the client. When they get back to the client, they're automatically encrypted and then handed the application. Trade-offs. This is really meant for operational workloads. You want to do it on limited return sets. If you're doing an analytical work set where you need hundreds of thousands of documents or system-to-system transfers, that's probably not the best target. Read heavy. The vast majority of use cases for our customers who are evaluating this is read heavy. 80, 90% reads, a smaller percent of inserts and updates. And you don't want to encrypt everything, right? Generally speaking, what we found is that it's the linking between certain data, right? If you had a representation of a checking account, if you said $6,432, that's not sensitive. What's sensitive is the thing that links that value to the customer. A lot of PII comes down to a relatively small number of fields. You certainly can do more. You can certainly make it more encrypted fields if you'd like, but it sort of becomes an anti-pattern once you get past about 10 or so encrypted fields. Performance. It's hard to emphasize how big a deal this is. We're at the 1 to 4x of plain text. That's an enormous amount of optimization that went on. So as a practical matter, 95% of the workloads came back in 15 milliseconds. And the vast majority between 3 and 5 milliseconds wall clock time. If you're doing bulk loads, if you do need to write millions of records, you take more of a hit. But in many cases, you can handle that with batch processing or things like that. The sweet spot is multi-threaded clients. In most web applications, that's sort of built in. Non-targets. So if you do need analytical workloads, if you do need those massive writes, potentially batch uses or batch use cases may make sense. Storage, there is a cost. So we're about 2 to 3x collection size. So in other words, if you've got a gigabyte of collections, you're going to need about 3 gigs of storage. We have something called the compact operation. It's a way of sort of occasionally trimming back the size of some of our internal search structures. Those are kind of workload dependent. We've got some more guidance online in our docs in terms of when that may make sense. But it does give a performance improvement. One of the things to sort of kind of give you a sense for the depth that we went to handle confidentiality, we have a slow query log in MongoDB. I think it's either 100 or 200 milliseconds. If queries take that long, they start adding up into our encrypted log, our slow query logs. Those are scrubbed. The performance analyzer doesn't get any special privilege. to see the data that you're working on. The real-time performance panel, that's stripped. The query profiler, the query plan cache, ops manager, cloud manager. There's no records of this in sort of the internal diagnostics that you'd normally expect. So there is a trade-off for that. But the advantage is that the server learns virtually nothing except things like time of insert or rough size of the document. It does impact staff, so staff support. So if you have something that goes south at 2 in the morning on a Tuesday, and you say, I'm in production, we've got a crash, help us figure out what's going on, we can tell you that disk load is up, we can tell you that CPU is max, we can tell you there's memory pressure, we can tell you that between this time and this time, you started really hurting. What our support staff can't see, no matter what, they can't see the queries that you're running. They can't see that sensitive data. Quickly, difference between client-side field-level support and Queryable Encryption. CSFLE is not being deprecated. We see this in some of the most mature production workloads. It's not being deprecated. Queryable Encryption is recommended for net new applications. We'll have these slides available later, but just some of the comparisons between the two capabilities. When to consider CSFLE, if you've got an app that's actually up and running already, you're already using end-to-end encryption, you've already got data in use encryption in place. Non-target workloads, so heavy bulk writes, heavy bulk inserts, those are probably better targeted for CSFLE. If you do need the per key, the key per tenant or the key per user, CSFLE is probably the sweet spot there as well. Tying it all together, what do you need today? You need 7.0 server, you need current drivers, shell and compass, I think actually for about a month now have supported the 7.0 GA, and automatic encryption. We make this available in all versions, but if you want the thing that automatically converts the query from sort of the natural standard language into, without any kind of helper methods or special functions, that's Atlas and Enterprise Advanced, including the free tier. Some of the stuff on the components and the licensing, pretty straightforward. I don't think these are surprises. We've got links to libmongocrypt and our core Python, Node, Go, et cetera, drivers in GitHub. This last bullet is the one, if you really want to dig into the details, understand the internals, understand the mechanics, take a look at the math, take a look at the background, the history of the academic work. I would start there. So we will end it there. Thank you so much.